Okay. So welcome to the second week of this course on combinatorics. And previous week we looked at the P-J-Hole principle and some related questions. This week we are going to look at some basic counting techniques, which will be useful for developing new techniques as well as for any question that you might look at combinatorics. Any of these questions will most of the time need some of these basic techniques and their understanding. So we are going to start with a simple question, and then we try to see how to develop this into a technique, and then that is the idea. Okay. So here is the question that a number of monkeys jumped across a small river from tree A to tree B. Okay, so we have these two trees, let us say A and B, and then the monkeys jumped from one tree to the other. Now, when they were jumping, 10 of the monkeys fell down to the river, and then they got wet, and then they swam across. What we know further is that the remaining 15 monkeys did not get wet. Now the question asks us to find what is the total number of monkeys that jumped. Okay. Now this is a very easy question, right? Any student of mathematics should immediately be able to tell that since we have 10 monkeys who fell to the river and 15 who did not, we have 10 plus 15, right, which is equal to 25, right? So 25 monkeys basically jumped from river, one of the tree to the other on the river side. Right? That is the answer that we all know. Okay. Now, let us look at a slightly different question. A number of friends went for a trip somewhere. Okay. Now, when they came back, 8 of them wore blue t-shirts and 11 of them wore red t-shirts. Now the question is that how many went for that trip? Now, is it possible to answer that this is 11 plus 8 is equal to 19? Well, in fact, no, right? Because what we know is that there were 8 people wearing blue t-shirts and 11 wearing red t-shirts. So we definitely know that there were at least 11 plus 8, 19 people who went for the trip. But now the question doesn't say anything about other people who might be wearing let's say yellow or green or other shirts, right? So the question doesn't list exhaustively, right, all the people who went for the trip, and therefore we really don't know whether we have more than 19 or not. So we cannot really answer it except saying that okay, there were at least 19. Now let us look at a slightly more different question. So we have a few classmates who went for a mountain climbing, right? Another trip. 6 of them had shoes, right? They were wearing shoes, and 7 of them had walking sticks with them, while 3 were barefoot. Right now, how many went for the trip? So here there are two problems, right? We don't know whether the question is exhaustive, whether it covers all the people. But even if, let's say that, suppose we are giving that the remaining 3 people were barefoot, we still don't know. Maybe the 7 of them who were having walking stick where precisely those having shoes and who were barefoot, or maybe some of them had something else like boots or something, right? So this question does not say whether there could be intersections between these people, or like whether there is some other thing. They were separate, 7 people, right? So these questions we don't know. So therefore we cannot really answer anything about this. So these three tells us something, right? In the first question we were able to answer precisely because we knew that both the sets were disjoint and they were exhaustive, right? So if we are given that if A and B are disjoint sets, and then their union, we can say, has cardinality equal to the sum of the cardinalities of each of them, right? So this is called the addition principle. So if we want to use addition to count things, then we can use this principle, but we require that they to be disjoint, right? So if A and B are disjoint, then we can find the cardinality of A union B is equal to cardinality of A plus cardinality of B. On the other hand, if you have more, we can still we can still use this, but we need the pairwise disjoint condition to be able to use this. So suppose we have A1 to AK are pairwise disjoint sets, then the union has cardinality equal to the sum of the cardinalities of the individual sets. But it is important to note that we were clearly saying that A1 to AK are pairwise disjoint, right? It is not sufficient to say that, let's say that there are A1, A2 and A3, and A1 intersection A2 intersection A3 is empty, right? So A1 intersection A2 intersection empty says that A1, A2, A3 are all together disjoint, right? They don't have a common element. But it does not say that A1 intersection A2 is is empty, and A1 intersection A3 is empty, and A2 intersection A3 is empty. So this is required to be able to use the addition principle. So we have a pairwise disjoint sets, then we can also count. So this is the generalization of the addition principle. Okay. Now, so here is a subtraction principle. Okay. So what is the subtraction principle? It says that if A is a finite set and B is subset of A, then cardinality of A minus B is equal to cardinality of A minus cardinality of B. So earlier we were looking at when we can add. Now we are asking when we can subtract. Okay. So we are saying that if B is subset of A, then we can find the cardinality of A minus B by looking at A minus B, cardinality of A minus cardinality of B. But B subset of A is very important. If B is not subset of A, this principle cannot be directly applied. So here is an example. Let us say count the number of positive integers with at most 4 digits that have at least 2 different digits. So we want to count the number of positive integers with at most 4 digits that have at least 2 different digits. Now one can directly count this. Okay, I recommend that you spend some time finding out how to directly count this, right, rather than using the subtraction principle, and then see why it is going to be better to use subtraction principle here. Okay. So how do we use the subtraction principle? So what are we given? We are given that we have the set of positive integers with at most 4 digits. That is what we are looking at, right? With some extra properties. So we can consider your big set as the set of all positive integers with at most 4 digits. How many are there? Well, we know that the smallest number with 5 digits is 10,000. So therefore, up to 9999, right? 9,999. we have integers, and they have cardinality exactly. I think I made the wrong tool. So like 1, 2, etc. Let's say 9, 9, 9, 9, right? And this set has cardinality is equal to 9, 9, 9, 9, right? So we have this many elements in our big set. Now we want to be able to find another set B with the property that if you subtract cardinality of B, we get what we want, right? We want to find out the sets. We want to find out the number of elements that have at least 2 different digits. Now, so the natural set that we can look at is all those integers with at most 4 digits, but having only one. There is no 2 distinct digits, right? So exactly the same digit is repeated for all these numbers. Now this is very easy to count, right? So what is B consisting of? It has all the numbers 1 to 9, right? 1, 2, etc. 9. Then it has 1, 1, 2, 2, 3, 3, etc. Right? Again, there are 9 of them, 99. Then you can have 1, 1, 1, 2, 2, 2, etc. up to 999. Similarly, 1111, etc. 9999, right? These are precisely those with 11122, etc. Right? Not all the numbers in between, right? So here we have exactly 9. Here exactly 9. Here exactly 9, and here also exactly 9. So this says that we have exactly 36 elements in B, right? So 36 numbers has this property that it uses only one digit, right? I mean repeatedly, but only one distinct digit is appearing. I mean unique digit is appearing. So therefore, we can find out the cardinality of A minus B, which says, right? So A minus B is the set of numbers with the property that we were looking at, right? Less than 9999, less than 10,000, and having at least 2 different digits. So what is this? This is 9999 minus 36, right? Again, wrong tool, sorry. 9999 minus 36. And what is this number? Whatever it is, 63, right? 9963. Fine. So we use subtraction principle to count this. But again, you can verify that if you can count without using subtraction principle directly, and maybe you can see that like this is much more efficient way to do the counting. Okay. So now, as I told you, we want the condition that B is subset of A to be able to use the subtraction principle. So I want you to come up with some examples that illustrate that B subset A is necessary, right? Otherwise, the counting will go wrong. So come up with some examples. It's very easy to come up with, but still think about it. Come up with a couple of different examples. Okay? So this is a homework. Now, let us look at another problem. So we already studied 2 different principles, right? Addition principle and subtraction principle. Now let us look at another problem. So count the number of binary strings of length k. So binary strings are the strings that we create with just zeros and ones, right? So example is like 0, 1, 1, 0, 1, right? Or 1, 1, 0, 0, 1, 1, 1, right? So all these are binary strings. Now we want to look at strings of length exactly k. How many are there? Now how do you count something like this, right? So you can try to find out like for like 1, for example 2, right? So for 1, if the length is exactly 1, we have either 0 or 1, right? There are two possibilities, and that is it. If you are looking at the length 2, then you have 0, 0, 0, 1, 1, 0, and 1, 1, right? There are 4 of them. Right? Now, once you do this, we can try to, like come up with a, an idea and then try to use some method like induction or something to prove this. That is one possibility. Now let us look at another way to look at this. So what we know is that we are going to look at strings of length exactly k, right? So we have a string of length k, means that there are k positions, right? Position 1, position 2, position 3, etc. Position k. So we have strings with k positions. Now, if you look at any position, what are the possible letters of that can appear here? Either 0 or 1, right? So at each position we have only the possibility to write either 0 or 1, right? 0 or 1, right? 0 or 1, 0 or 1, right? So every position has exactly these two possibilities. Now I can put 0 or 1 at the first place, and without worrying about what happened in there, I can put 0 or 1 at the second place, one of them, right? Exactly one of them I can put at each of the k different places. So this says that I have exactly two choices, right? Two possibilities for the first position, 0 or 1. Exactly two possibilities for the second position. And the first position, whichever I choose, I can still choose the second position without worrying about what happened there. So they are basically independent. So I can decide this independently, right? Like what to write here. So therefore, what we know is that if I have two choices here and two choices there, then I have 2 into 2, 4 possible choices for the strings of length 2, right? So I can basically multiply the choices available at the position 1, position 2, etc., position k, and multiply them together to get the number of strings. So the number of strings of length k is going to be 2 into 2 into 2 into 2, etc., up to k times. So that is 2 raised to k. So we immediately get that the number of binary strings of length k is equal to 2 raised to k. So now let us look at another question. We want to find the number of 4-digit numbers starting and ending with an even digit. Okay. So how will you calculate this? Again, I want you to pause the video and think about it for a few minutes if you want. Right? Maybe you can get it immediately, but think about it and then find your own answer. And then if then you proceed, right? So how do we do this? So we have 4-digit numbers, and then it can start and end with even digit. So this puts some restrictions on what are the possible numbers that you can use, right? For example, if you are looking at the first position, right? The first position, can you use, let us say, right? Let us say that you are using the 4 positions are here, right? Now, in the first position, can you use like you are only allowed to use even digits. So therefore, what are the even digits? Like 0, 2, 4, 6, and 8, right? But 0 cannot be used in the first digit because we are talking about numbers. It's not string, right? So therefore, we are not allowed to use 0. So we can use 2, 2, 4, 6, 8, right? Any of these numbers we can use here. Now, it should start and end with even digits, but that doesn't say that the middle digits can be anything, right? So middle digits can be any of the possible numbers 0 to 9, right? So therefore, there are 10 possible choices here, right? Similarly, third digit can also be any of the 10 possible digits. What about the last digit? It must be an even digit. So what are the possibilities? 2, 4, 6, 8. But here we also can have 0. So there are 5 choices here, 4 choices here. But now these can be independent, right? No matter what I choose at the first place, I can choose any of the 10 digits in the second place. So I have 4 choices here, and independently I have 10 choices here. So 4 into 10. Similarly, another independent 10 choices here. I have another into 10 and into 5. So therefore I have total number of choices is 4 into 10 into 10 into 5, which is equal to 2000, right? So we have exactly 2000 numbers with this property. Okay. Now, this tells us a general principle which we call the product rule or fundamental counting principle. So what does this exactly state? So we can state the fundamental counting principle as follows. So consider a finite sequence of decisions. Okay. So sequence means that, in the first time you make a decision, then there is another place where you can make another decision, right? This way. So consider a finite sequence of decisions, and suppose that the number of choices for each separate decision is independent of the previously made decisions. Okay. So the decisions are made in some sequence, and I make the first decision, then second decision. And when I take the third decision, I want to make sure that all the previous decisions does not affect the choices here, right? So the choices are independent of the previous decisions. Then the total number of ways to choose the sequence of decisions is the product of the number of choices at each stage. So we have a finite sequence of decisions, and the choices, the number of choices for each separate decision is independent of the previously made decisions. Then the total number of ways to choose the sequence of all the decisions, right, is the product of the number of choices at each stage. So this is the product rule. Now we already saw 2 applications of product rule, but let us look at a few more, because it's a very, very important rule, and we will need lots of applications of this in the following days. So here is another example, right? Find the number of positive integer factors of 1500. Okay. So how can you use product rule to find out the number of factors of a number given like 1500 here? So again, try to work it out yourself. Stop the video, watch, and then get back. So how are you going to do this? Now, what we know about 1500? 1500, I can write it as 3 into, right, 5 raised to, so how many, so I basically I look at the prime factors, right? So I know that there is 5 appearing 3 times, right? 5 raised to 3. And then how many times 2 is appearing? 2 raised to, let us say, 4 times, right? Is it correct? 3 into 5, 15. Then I have 25 into 4, which is 100. Then another no, 2 raised to 2. Okay. So 2 raised to, how many are there? Not 4, right? Where is the eraser? Right? How many are there? 2 raised to 2, right? So 25 into 4, which is 100, and then 3 into 5, 50, right? So 3 into 5 raised to 3 into 2 raised to 2, right? So this is the prime factorization of 1500. Now, how can you use the prime factorization now to find the number of positive integer factors. So if you look at any factor, we know that the factor is basically a product of the possible subset of the prime factors, right? So therefore we can just look at how many such possibilities are there, right? So since 3 is appearing only once, my choice is to have either 3 to appear in the factor or not, right? So the power of 3 in the factor can be 0 or 1, right? So I can have 3 raised to 0 or 3 raised to 1, right, as the possible factors. Similarly, I can have 5 raised to 0, 5 raised to 1, 5 raised to 2, and 5 raised to 3, right? There are 4 possible choices for 5, right? And then I have 3 possible choices for 2, right? 0, 1, or 2. So therefore, what can I say? I can say that, like, if this number is given, then I can find out there is 2 into 4 into 3, right, which is 24 possible factors. So these are the number of possible integer positive integer factors of 1500. So here again we use the product rule, right, because the choices were independent, right? The 3, I'm choosing 3 to be one of the factors or not is independent of my second choice, right? How many 5s I am going to take, or how many 2s I am going to take. So therefore I can use this. So I get the answer 24.